Welcome to the Guardian Group podcast series. The Guardian Group, providing extraordinary solutions to today's exceptional problems.
Hello, podcast fans. Welcome to another episode of the Guardian podcast series. I'm Todd Comodine, your host. Usually joining me is Rick Murrah, but he is on assignment, so he will not be joining us today. So I'll solo this one today, and we're going to talk about buried passives and testing thereof. You know, those pesky components that are involved in manufacturing today. And so what is a buried passive when we talk about these? Buried passives are a component or a feature that's integrally manufactured into the printed circuit board. These are usually typically resistors, capacitors, and more recently, we do see some inductor circuits. Resistors, capacitors, inductors all do different functions. They can be by themselves. They can also be used together to create different types of circuits, filters, timing circuits, heater circuits, and a wide array of things. And they are sometimes built into the PCB now rather than using the discrete components on the surface of the boards, being an analog type wired leads or surface mount type. So the first thing we want to talk about is resistors. And when we talk about that, I wanted to kind of give us a little rundown on the Ohm's law theory again. We've talked about that in the past, and Ohm's law is basically the relationship between voltage, current, and resistance. And using a scenario of everyday life, voltage, we can picture this as a river. I think this is a good one. It can be small or it can be very large. The smaller the river, the smaller the voltage, larger river, more voltage. And then when we talk about the second component of it, we talk about current. And here we can visualize current as the speed of which the body of water is flowing. A slow-moving river, for example, doesn't have a lot of current. Same with the electrical property current. However, this is unrestricted, and if it rains, more water is introduced to the basin or the river, and the speed of the stream or river increases, thus more current. So you're thinking probably, well, where's the resistance component in there? Well, you have to think about it. You have to have all three attributes involved in the law because you can't cheat the law. So if we have voltage or the river, the size of it, and then we have it moving, the current, well, you got to have some resistance. So, okay, we can use the earth or the riverbed, rocks, trees, branches, whatever's slowing the river somewhat is developing the current, because if you don't have all of the three, the formula doesn't work. Therefore, no current will flow if you don't have any resistance and then or any water or and so on. So when we talk about the last thing, when I said riverbed or whatever, the final attribute, you know, we can, in the laws, add resistance. In our scenario, think of this as a dam on the river. Now we have slowed the river down. More resistance we put against the current, the slower or lower the current is. So by using this law in nature, we can actually adjust the volume, movement, and speed of the water by a dam. So if the dam slows the water, the current slows, just like if you add more resistance in a circuit, your voltage or amount of water in this case is constant, and you increase the resistance, the speed or the current is going to slow down. Conversely, if you open the spill gates and lesser resistance is in the equation, more current's going to flow. That's kind of a everyday scenario when I talk about voltage, current, and resistance, to put it in everyday terms that people can understand easily. The other thing is when we test capacitors, well, what are capacitors? There's a couple types of them. You have your ceramic and paper caps, and then you have your electrolytic. And the ceramic and paper caps a lot of times are filtering type caps. And think of those as filtering our water supply. They remove maybe unwanted debris from the water. Ceramic and paper caps are commonly used or commonly thought of as filter caps. They can filter unwanted noise or signals when we have in our circuits. The others are the electrolytics. These are the polarized caps. These basically can hold a charge. So looking at this and creating a scenario for that, think of that as a water tower on our river. So we can draw water out of the river and we can hold it in the water tower until needed. And then when triggered, we can dissipate that water rather quickly. That's the whole idea of ceramic caps. And they can be used to create timing circuits and a lot of cool little features. The other thing is when we talk about is what are inductors? Inductors are coils, can perform quite a bit of different functions. We see them on circuit boards as wound traces, sometimes for called heater traces. We sometimes see them as being a timing type circuit where you see long traces, wiggly lines, and things like that. And these are working on timing of circuits. We see this really a lot in microwave and extremely high speed circuits in laminates for space and such. The coils can also be step up or step down transformers where they can take a voltage and increase it or decrease it depending on windings around the core of the coil. And they can also be used in conjunction with capacitors and resistors to create filtering, which we use those for, sometimes referred to as band pass or band stop. And I tried to think of a scenario where I could think of how a transformer or a coil scenario would work in my water scenario. And the thing I thought of is kind of like a condenser, or if you have two bodies of water, you have the ability to create, because what it does is a lot of times with primary and secondary parts of a transformer, you are inductively, or you're doing a transformer coupling where you're actually physically not moving the voltage directly from the primary to the secondary. You're doing it by inductance. And so the thing that I would say that would be explaining that is you're leaving unnecessary or what you don't want behind. And in a case like that, in distilling or something like that, we use steam. So think of, you have a couple of bodies of water and we're moving some water from one side to another. If you have the same amount of coils from side to side, you will move the voltage over, but you will leave parasitic components behind. And therefore, if you have more windings on one, the primary or secondary, it will increase or decrease the amount of water that we're inductively transferring, let's say, to the pond or to the other tributary from the main. Kind of an interesting scenario that I thought up, and there might be some holes in it, but I thought that's kind of beneficial for the explanation. So that talks about our resistors, caps, and inductors. So with that, we have to figure out how we test that. So a lot of times, back in the day, we had buried resistors in the form of a carbon film where a carbon screen was put on the board. And this worked fairly well, but it was fairly also unpredictable, depending on lamination cycles and heat. Trimming of the resistor could cause erroneous results. And we found a lot of times that just the heat of lamination caused, like I said, the unpredictability. So trying to predict the resistor output after lamination cycles was difficult. So they went into another material type scenario where they use a resistive laminate where there's copper on the outer surface and a resistive laminate under that. And so to create the necessary resistance, you etch off a certain area of the copper, exposing the resistive material, and based on the square, you will develop that resistance. It's very predictable. And if etching and everything is working as designed, you will get a very, very strong resistor out of that. When testing these things, a lot of it now, like I said, is in the material type resistor. And a lot of it nowadays is done via flying probes. It still can be done on fixture testers, but there's a lot more cost involved in that. And you have, fixtures, and if there's a change in the program that might change the footprint of what's required in the fixture, then you've got a scrap fixture and you have to re-drill that thing and start all over, and that can be fairly expensive. With the flying probers, you don't have that problem. You basically program the board, and it can be done prior to the boards coming to be tested. And in the case of the flying probes, you can actually do the program changes on the fly on the machine if there's a resistive change or something that needs to be adjusted. You're not scrapping a fixture and starting that all over again. So when resistors or capacitors are tested, we can do them in series. So we have a resistive total. We can do them in parallel, which there's resistive circuits in that, or formulae, I should say, in that. Or we can do a combination of both. The system, when the CAM software creates the programs, it does the algorithmic calculations for resistive total, whether it's series, parallel, or a combination of both. So you know what that number is going to be when the boards come to test, and you can also put tolerances in there so that your pass or fail has a range. And when we have the boards to test, if available, if the landing pads are available, we can actually test the individual components themselves. And sometimes we can do this, on the layer level before lamination, because sometimes engineers want to know exactly what each resistor is so they can tailor their circuits if they have to make adjustments. But the only caveat that really is if you have what we call a circular net, where you might have resistors and they're in a kind of in a circular net where there's only maybe one point available for us to test. So you don't have the second point of the test, so you can't get an accurate measurement. And the other thing that you have to have at least, if it is a circular net, you need to have at least 2 test points, and you need to have them on either side of the resistive or capacitive components to get an accurate measurement. Otherwise, we're kind of up the creek again without a paddle, because we can't get an actual resistive or capacitive reading. So when we talk about testing and flying probe, Guardian has an array of flying probe testers that can provide this buried passive test. And we also have the ability to test also inductance, high pot, if that was a requirement. We do a lot of high pot testing. And we can also do impedance, TDR, with some minor changes to the machine. They all can do it. It just depends on the customer level what options you need. These use a featherlight, very non-abrasive, non-aggressive type of probe, and we do actually have needle probes too that can get into the very, very tight arrays or component packages that we see today. So, if you're looking for solutions on your own rather than having us do it, which we're obviously glad to do, give us a shout, and we can explain what options do we have and what equipment we have as far as our lines of flying probers that can take care of this. The other thing is when you're doing very passive testing or testing, it all drives from software. And what is the software able to do? How does it perform the tests? And Guardian supplies our own proprietary software. It's called FPX, and we have options for many different types of tests right out of the box. And it's just basically a licensing type of thing. Add more options to your license, and it's that easy. It's no, in a lot of cases, it's not a hardware thing, but some of it with impedance and inductance, we do have different meters that have to be added to the machine. So this all can be discussed with sales people with our group. But anyway, when we do the test, the machine goes out and does the interrogation. This can be combined with the standard opens and shorts test as well. So it's not like you have to take the board off and put it back on to do a different test or load a different program. We do the same all at one swoop. So we go out and we do our opens and shorts test normally, and we also do the buried passive test. A lot of times the buried passive test is done first to make sure that we don't have any problems. And so it goes out, interrogates the board, makes a notation in the system of the resistive values or capacitive values, stores those, and at the conclusion of the test, we get our pass and fail. And it'll print out a tag if you so desire, and it also logs that as a report option in the system. So you can actually go back and read the values, see where adjustments might be made, or see where maybe a systemic fault is happening, or you're seeing an entire array of the resistors all low or all high. Maybe there was an etching problem, something like that. But that's all available to the operator or design engineer. And this can be exported in an Excel or a CVS or CSV format so that it can be read into diagnostic software or statistical process control where SPC can be monitored and so forth. It actually, and the thing about doing these passives while doing all of the other tests, like I mentioned, you're not having the extra operator intervention in the machine of taking a board off, changing a test, putting the board back on, doing it again, less handling. And that works both ergonomics for operators, and it also lessens the chance for handling damage, which by and large is a very large attribute or Pareto in manufacturing scrap in the manufacturing facilities. So for the software, I mean, these options are all available with the equipment. FPX is currently always evolving, and support's available almost 24/7. We can log into the machines remotely and diagnose what might be going wrong or make adjustments if something isn't happening. We're here to help you. So inclusion, what did we talk about today? Well, we talked about what are the buried passives. We talked about resistors. We talked about capacitors a little bit. We talked about inductors, coils, and how they can interact with each other. Gave you a scenario using Ohm's law and a daily life scenario of what voltage, current, and resistance is, how they affect each other. What do we do with testing? How do we get in there? What can we provide when we do the test? We talked about the outputs, the reports that we can generate. We talked about equipment. We talked about the availability of how we can help you and also our support. And with that, I have covered most of what I wanted to today about passives. It's a scenario in the manufacturing world today that's only going to increase. And hopefully the equipment can perform all the tests that you need. And as the component packages get smaller, our ability to test those moves along with it. So with that, if you need any more information, drop us a line at info@guardian.com. That's info at GARDIEN.com. Visit our website at www.guardian.com. You can click on the equipment tab to look at our equipment, and you can also look at our FPX software. And we also do have a few other lines. We do supply fixture testers, and we also have a line of handling equipment should you be deciding that you need to maybe make some adjustments, automate some handling to lower possible injury rates or material handling scrap and such. And so stop by, give us a look, and give us a call. With that, Todd Comodine, your host, closing out this session of the Guardian podcast on buried passives. Hope you have a great day, and we'll talk to you next time.